Now let's build a little bit more of a serious program using a Mnist dataset. Um, again, you can load this dataset from TensorFlow. Here is the location of the TensorFlow. And if you were to go to that site, hopefully this won't change that much, but here is a catalog. If you were to go to your catalog, there are many datasets that are out there that you can search for the datasets and then pick a dataset that of your choice. Here, as you can see, I'm looking at the Mnist database, Mnist database, that has, you can get to see the test, train dataset, and here is a way how you can get the dictionary of images and the labels. Um, and then it also shows a nice example of what that dataset is. This is something that usually you would use to test out some new frameworks. And then all the code is available at this location here. Um, and then if you want to get more details of the dataset, here is the URL that I just showed. Okay. Um, and then, by the way, if you were to go to this site and then search for Python, you also get to have a small little example of how to load the data. And we're going to do all that in this notebook, where we're going to be training a deep neural network. Um, for those of you who don't know Mnist data set, it consists of images that are 28 by 28 with one grayscale. Um, and then the data itself has different handwritten numbers. For example, 0, this is one of the image, and the label would be 0. And you will have many other images with 28 by 28 grid. Perhaps this would be 5 with the label 5. So these are the images, and we are going to train a deep neural network with these images as inputs, so that your deep neural network will know how to learn to detect what integer it represents given a handwritten image. Okay. With that said, here's a notebook. Again, usual imports. I want to get them. There are a couple ways that you can load the data set in Python. Either, as you can see in the first cell, that I'm loading tf.keras.datasets, Mnist, and then I can say load data. That will give me a NumPy array of xtrain and ytrain, xtest and ytest. And then when you load the data set, these gray images that you would like to, you may want to normalize them to a maximum of 0 and 1. So if you divide by 255, as each of the integers may go from 0 through 255, you will get a normalized image. So for those of you who didn't understand what it meant, was here is a cell. Each cell will have a pixel value, suppose 50, 255, 0, 128, and such. And you would like to get the neural networks to have a 0 to 1 normalized input. So if you divide each of the cell by 255, so you will get a grid which is normalized to 0 and 1. And that's what's happening here with xtrain and xtest. I'm dividing it by 255. Here is the next cell, shows you another way of how you can load the data. You can get the information. You can, let's try to run this as we are working through. As you can see here, VS Code shows that it took 1.4 seconds, have 6,000 records with 10,000 test data set. The same thing would be here, which I'm not printing it, but it would be the same information if you were to use the previous way of loading the data. Once if you load the data, I have a small utility that you can give it a number or the image index. It'll print the number, and then if you have the prediction, it'll also show the predicted value. So you can take a look at this plot, and it is just that I'm randomly taking one of the indices, for example 777, and the image happens to be 8. It shows the label, and since I'm not passing in any of the predicted value, it doesn't show anything. And we will see what that means later on. So here I'm building a simple sequential model with first layer being flattening the inputs 28 by 28 into a linear array, and then feeding it to a dense network of 128 um, with activation ReLU. Dropout is something that you would use to reduce the um, overfitting or regularization parameter. That means um, you may already know what dropout means. And then we have a dense of 10 output, which activation is softmax. So depending on the way how your input learns, your output would be a softmax activation of 10 outputs. So let's take a look what that looks like. So you have a input to your deep neural networks, and then you flatten it into a linear array, and then you have that gets into 128, 1, 2, 3, all the way up to 128 layer input, and then the dropout means 20% of the times some neurons will be dropped out, and then this layer gets fed to 10, 1, 2, all the way up to 10, and then this is the softmax output. So and then we will feed the Y during the training, and then softmax max, as you understand, that one of the numbers will be maximum, so you would use np.argmax to determine which one of them, what is the highest probability that this image seems to represent will be the output. So for example, this will be the probability of 0, 1, 2, all the way up to 9, and then one of them, if it happens to be 8, perhaps if your algorithm is working really well, it might have a probability being the highest here, perhaps 0.7 of something, and everything else will be a lot less. So if you take the NP argmax, it will give you the index which has the maximum value, and that's what you would predict as the number. And then we will build that model, and then we will do a prediction just to see, without any training, what kind of expectation that we get. This is the image 0, label is 0, and your neural networks predicted it is 4, because there was not much of a training that's happened. It is using the default weights. Now let's go back and compile and do the evaluation once more, and then right now we are getting about 7% accuracy, which is not great. So now we do the fit with the training module with 5 epochs and 8 seconds. Let's do the evaluate on the training module. Now evaluation seems to have an accuracy of 98%, and then if we evaluate it on the test data set, we are getting a test data set of 97% accuracy. Now let's go back and then take a random of 5 values and see if we trained a model that can predict pretty well. So 9 was predicted, and let's see, plot L with we need to get P X test, Y test, and then the index that needs to be 0. Let me take I comma L, let me enumerate P, and then let me pass in I. So here is a little bit of a correction that 7 was the predicted, 7 is the correct value, 2 is what was expected, and we pretty much are predicting the handwritten digits into correct value. So congratulations that you have built a real neural network to train the model to detect handwritten digits into corresponding classes.